Welcome to another Friday Lunch and Learn sponsored by the Tampa IIBA and Clifford Gray. This week we're gonna talk about simulation not only because it's my background and how I learned everything I know about business analysis, but also because doing business analysis involves or requires exactly the same skills you need to build simulations. I know because I did simulation first and then I moved into more generalized BA work and I use the exact same skill. So I've done simulation and business analysis in all these industries, and I'm sure you can think of many more industries where it's appropriate to do a simulation. For example, science is a huge one, scientific research, movies, video games, and entertainment more generally, and so on. So, really, it can be used in almost any industry you can think of. Why do we do this? To explore options that would be too dangerous or expensive or inconvenient to do. There are some things you cannot measure, but you can calculate them using simulation, and you can use the calculated values in feedback and control systems. Um, when you can't do experiments like on the formation of the universe, I mean, you can't run that 5 times before lunch and 3 times after. You have to play with it in a computer to investigate a lot of options and to investigate the range of different outcomes you can when the internal events are variable. So there are three major kinds of simulation. There are analog that are done with the electrical, mechanical, or fluid components, or mixes of those. There are continuous simulations, which are usually models of physical happenings, and they're based on differential equations. And the kind that are most germane to business analysts are discrete event simulations. And those are akin to the kind of operations you investigate and automate in the course of doing BA work. Now, obviously, you can have hybrids of all these, and I've done those many times in the past. An example of a mechanical simulator is these old link flight simulator trainers they used to make. That one's at a the Evergreen Air Museum in Portland, and I think it's sitting under the wing of the Spruce Goose. That is the San Francisco Bay model that is in Sausalito. That is a really cool place. The water area itself is about an acre in size. So that's totally an analog mechanical simulation of a kind. If you want to do electrical simulations, you can take advantage of the fact that there are many physical processes or realms that are described by similar equations. So if you build an electrical circuit with the same characteristics that mimics the physical system in question, you can get a pretty accurate simulation of those effects. That is a more formal way of communicating the same thing with the actual variables and so on. And again, you can have hybrids. So there are a number of applications you can do for this. Design and sizing is figuring out how much or how big you need a system to be or process equipment to be, or how many people or facilities you'll need to generate the amount of output you want. Real-time control operator training, economic analysis, and process improvement are all different things we can work on. The architectural considerations are a big part of what I'll go through in this presentation. So that is two major kinds of simulations. The one is a continuous simulation. It's the internal heating of a block of steel across a cross section. The other is the flow through of entities through a multi-phase process with cues. I've written these things up. If you want to find the simulation or these slides and follow these links, you can go to my website at rpchurchill.com, go to the portfolio page, and the fourth article down is presentations, and it'll be at the bottom of that list. This video will eventually be linked there also. So you can think about a fluid system or any kind of a physical system, and this isn't germane to BA specifically, but it talks about all the different things you need to know to build simulations. So we can describe different characteristics of the system in a series of differential equations, and then we can solve them simultaneously using a matrix. And just to show you an interesting phenomenon, you'll notice that this matrix, since everything is connected to everything else and to outside Saddam, is symmetric across this diagonal here is shown in blue. So the kind of light red squares on the opposite of each blue are the same. Same goes for the kind of foam green ones, and same for the purple ones. So you can rearrange those and solve that matrix by only looking at half of it, or a little more than half. And that means you can do fewer mathematical operations to grind through this thing. If you're using a really small matrix, it's not that big a deal. But if you're using a much larger one, for example, to solve a system of these equations, here's the same block of steel I showed you earlier in that nice graph that was animating its way upward. The matrices get a lot bigger. They're symmetric and they're banded, and you save a lot more time rearranging them for greater efficiency. So if you have a more complicated system, these things can be connected arbitrarily to anything else, but you can rearrange the order in which you define or number the nodes or any of the elements so you get the tightest possible man. If we want to talk about discrete event simulation, they do things in time order. They process one event at a time and also test for wake conditions. Unlike continuous simulations, which tend to run at fixed time steps, so they'll grind through 1 second at a time, or 1 minute, or 1 hour, or 100 years. It doesn't really matter. But discrete event simulations, you can have 50 things happen in a minute and then nothing for 8 hours. So during that 8 hour period, you don't have to grind through and do nothing in 1 minute intervals. You can just skip it. Also, you process events kind of qualitatively. This shows how some events are happening along a timeline, and this shows the nature of the event. So if we follow the blue entity coming into a queue, we see the change of state of the queue. So the blue enters, then we pull a green one from the queue that's gone now. The queue's obviously moving left from right. Um, we then pull from the queue so that first green one's gone, then enter another item in the queue. Then we pull the blue one from the queue. And that's a big part of what um, discrete event simulations are used for. So I'll show you an example of a running simulation. This is written in JavaScript. It can be written in any language. I've written full-blown simulations and tools to generate simulations in 6 languages probably. And in these you can change process times. You can change the percentage of times that things go from one process to any one of many different destination processes in different calculations and transformations can happen at any phase. And you can imagine this being any arbitrary business process in banking, document processing, computing, anything else. So one of the architectural concerns is interactive versus fire and forget. So an interactive simulation like you'll do for training or to adapt to changes in the environment will take ongoing inputs and then change its behavior. A fire and forget, you just start it, it runs, and it finishes, and that's that. There's an example of two different kinds of air defense missiles. An interactive one fires, and then the a ground station has to continually track the aircraft and giving commands to actually hit the aircraft. A fire and forget missile might work on infrared. It'll lock onto an aircraft and it will just chase it down on its own. So once you fire it, no ground station has to talk to it anymore. And there are pluses and minuses to doing it each way. That video, which I won't run for you, um, is of a weapon system I trained on in England when I was a young pup. It used an interactive command guided missile. I also used that cool helmet that the video talks about. There is an animation you can run up to show how this works. This is of a border crossing. Again, this is a fire and forget simulation. You just run it and look at it, and you cannot interact with it. For here's another example. I built nuclear power plant simulators for a while, and those are highly interactive. So what they would do, this is a shot from the movie China Syndrome. That is Jack Lemmon standing and the back of Wilford Brimley's head. That was actually filmed in a simulator and not in an actual working control room. But it looks great because they build a total mock-up, everything in the control room. As, instead of hooking it to a real plant, they hook it to a simulation, and you pick what in the plant needs to be simulated by, whether it is affected by or affects any controls or indicators on those panels. So real time versus non-real time is another consideration. Real time obviously works at the same rate 1-to-1 as real time. For a solar system simulation that might run 4.5 billion years, obviously that's a non-real time. almost always you want to run things much faster than real time if you can, but some models are much slower, like global climate model. Single platform versus distributed is another consideration. If you look at something like SimCity shown on the left, that is a single platform. It's one program, runs on one computer, it's self contained, off you go. I've spent about half my career doing each kind. On the left is a plant-wide integrated control system that's controlling all the process equipment in a steel mill through multiple levels and up through a plant-wide tracking system and up through all the business systems needed to process orders, manage money, personnel, and so on. So the block there in the gray area, the blue one that's slightly larger, that's the model predictive control systems to control furnaces that I used to build. So there are some distributed simulation protocols. A big one is high level architecture versus distributed interactive simulation. The biggest difference between them is one is centralized and one is peer to peer. Also, massively multiplayer online RPGs is another form of distributed simulation that's used for entertainment. But you need BAs to build all those things or people with the same skills as BA to make those happen. All right, so deterministic versus stochastic is another very important architectural consideration. Deterministic, and this is most continuous simulations. If you have a given set of inputs, you will always get the same output. It'll always produce a single point result. By contrast, a stochastic simulation will generate different outputs every time you run it, as long as you give it different random number seeds. So, because you need to be able to um, repeat experiments, you want to be able to get the same result every time if you run it with the same random number of seeds. So you get the same random outcomes all the way through the model run. And there are examples of different kinds of systems. I find it interesting, especially with the epidemiological models that have been so in the news lately, that they report their outputs with a single value. And that is wrong. One of many things that are probably wrong with them. Um, Here are some information about Monte Carlo analysis. It's basically based on the famous casino in Europe. There are some links I put in here about Poisson functions, and there are a lot of write ups on my website that go into this in more detail. The Wikipedia link talks about the very famous people who were involved in this early on, and it was an application that was just waiting for the advent of digital computers, and it was some of the first programs ever written were to do this kind of work. If you want to look at random outputs for different kinds of processes, here's just a theoretical example of the kind of outputs you can get. Um, they're all different shapes and distributions of outputs, and they all can be put together to build up a Monte Carlo or discrete event system. Um, Here's an example of running a model predictive control system for controlling a steel reheat furnace. So on the right, you see an actual installation on model in Korea, and it's two 800-foot long tunnel furnaces with long sections that swivel so you can transfer steel slabs up to 150 feet long from one to the other. The reason they did that was because there are two thin strip casters and only one rolling mill. So on the right, here's a PC simulation I did. The lower depiction shows the temperature as it is right now. The upper depiction is shows the outcome, the discharge temperature of every spot on the slab if you don't do anything different. Um, the point of this is that you cannot measure, like I talked about before, what's going on inside the piece of steel, but you can simulate it. And then you can change both the travel speed or residence time of the steel in the furnace, or you can change the temperatures in different sections of the furnace to get the outcomes you want. Here's an animation of the same thing without the prediction in this case. And this is a shuttle furnace and not a swiveling furnace. But this is what I was doing with PCs in the mid to late 90s. So other contexts for simulation, whenever you're automating a process or building a computer process, in some ways that is like simulating activities that either can be or used to be done by humans. You're automating a lot of things. You can think about business processes as human in the loop simulation. So you're using all these same skills. Now, if you remember previous weeks, I've gone through the whole process. Um, Intended use, conceptual model, requirements, design, implementation, and test and acceptance. So it's the same process for doing both. If you're automating the interaction of a human with a computer's user interface. That's just robotic process automation. Nowadays, we use tools like UiPath and Selenium to accomplish that. We do it for automation, we do it for user acceptance testing, but none of it's new. I did it back in the 90s using FileNet, and I'm sure it goes back much farther than that. So we're getting near the end. What do we need for simulation? We need the ability to do lots of calculations. We sometimes need a lot of memory to store a lot of information and output. We need uh, accurate and authoritative and obtainable input data. I can talk about data quite a lot. Richard certainly did in the 20 presentations he gave before I started. You need to have valid behavioral data that is accurate descriptions of what happened and what transformations and calculations are done. And you need to have the right level of detail, and you need to generate output you can do something with. If we want to change things, so we need more computing resources, what could we do? And this talks about the limits of simulation. So if we think about a global climate model, think about the resources you need just for a moment. The surface of the earth is 196,900,000 square miles. So if you want to have nodes that are a mile on a sign, not to mention how many you might need vertically to simulate what's going on underground and in the water and in the various levels of the atmosphere. You need some multiple of 200 million nodes. That's a big honking computer and a lot of memory you need. So every simulation will necessarily involve some shortcuts. You can also make the time steps as short as you want. I note the current limit there because an assumption in many simulations is perfect mixing of fluids. And if you make the nodes too small or the time steps too long, so that more stuff is going through the node that can be stored in the node, you ruin the conservation of mass and energy in the simulation and make it less accurate. So if you're gonna simulate an atom, what would you have to include? Think of all the different particles. Think of the vibration of the whole atom, and then think of all the quarks that make up the particles. And every one of those quarks has charm, flavor or strangeness, spin, up or downness, and some other characteristics. And they all have a location and a momentum and a direction. And if you're simulating that in a digital computer, the calculation and memory representation requires a whole bunch of atoms to make up the memory chips and so on. So, if you wanted to simulate the entire universe, you need a computer that's way bigger than the entire universe. So, the universe can only be an analog simulation of itself. There I link a couple fictional references. One is a book I talk about this in more detail in the nerdy Star Trek reference blog post that's linked there. So this is the final slide. If we want to make simulations accurate, we need accurate data that we can actually get. We need to make sure the effects included are smaller than greater than the margin of error. So it doesn't matter if we're trying to do something that's lost in the noise. If we include a new fact that changes the entire outcome, and this happens all the time in climate models, you have to wonder if they're any good. And then you have to be able to match known historical cases. We'll talk about tuning models and doing VB&A going down the road a bit. But for now, I'll leave you with the idea that all simulations are wrong, but some are useful. As always, feel free to contact me if you have any questions or if I can do anything for you. Thank you for joining us for another week. And Cliff, I'll let you take it away.
Yeah, as always, happy Friday. Hope everyone has a great weekend, and we look forward to seeing you again.
All right. Great weekend, folks. Thanks.